Hi, welcome to Physical Science 4.2 on heat and temperature. Today's video is going to be very different because I'm going to show you a video inside this video. It's long, it's old, it's from Classroom Discovery years and years and years ago, but it's really good at explaining the differences between heat, temperature, and thermal energy. So stay tuned.
Heat is everywhere. In cars, in your body, even in ice. There is heat in every object in the universe. The human eye cannot usually detect the heat that objects emit. It is infrared energy, part of the electromagnetic spectrum that's invisible, like X-rays and microwaves. But a thermal imaging camera detects heat energy and converts it into colors we can see. Here, white is hottest, then red. Green is in the middle. Blue and black are coldest. These people are in a hurry. See their white-hot hands and faces? This is what we look like when we're drinking cold milk or hot coffee. To measure the precise heat of an object, we use temperature. Our lives depend on it. Our bodies, buildings, cars, all need to be kept at certain temperatures. Too hot or too cold, and they'll be damaged, even destroyed. But it's an elusive quantity and pretty hard to estimate. Let's ask a few people what temperature they think it is today.
Hard to say, really. Cold.
It's quite hot today. It's about 13 degrees C.
I don't know, I've only just got back from Australia, so I'm finding everything very cold indeed. 10 degrees, something like that.
18 degrees or something, it's pretty chill. No, what am I talking about? 14 degrees, something like that.
The way we tell the temperature is through our skin. The problem is, what's hot to one person is warm to another. This is all right for everyday things like testing the bath, but to measure things scientifically, we need a more reliable instrument than the finger. The foundations of temperature measurement were laid by the great Galileo back in the 16th century. He was studying the effects of temperature and struck upon one of its fundamental properties. As most things are heated up, they expand. When they're cooled, they contract. Galileo made an instrument which had liquid at the bottom and air trapped at the top. He noticed that when the air was heated, it expanded and pushed the liquid down. When it was cooled, the air contracted and sucked the liquid back up. Galileo had made a primitive version of the thermometer. It demonstrated the effects of temperature, but didn't tell you what the temperature was. For that, a scale would be needed to measure how far the liquid had moved. When you're designing a scale from scratch, where do you start? How do you decide where the top and bottom points should go? There was one low temperature that scientists had established was constant, the point at which water turns to ice. This became the zero on the scale. Next, they needed a fixed high point. Again, the answer came from water. It always boils at the same temperature at a given altitude. The scientists just divided up the gap between the two fixed points and they had their scale. But that's where the troubles began. In the early days, different thermometers had different scales, and there was no standardization. Then there was the puzzling question of what liquid to put in the instrument to measure with. The scientists had to find something which would remain liquid at the temperatures when water boils and freezes. They tried everything from wine to olive oil, but these expanded in inconsistent ways and boiled and froze at inconvenient temperatures. There was one fluid which did fit the bill. It was a liquid metal with magical properties known as quicksilver, or mercury. The good thing about mercury is that it expands in a very regular way over a wide range of temperatures. But the expansion is so small that it's hard to see. So a long, thin tube of glass would have to be made to register any change. The glass blowers of the time couldn't master it. Then in 1714, along came Daniel Fahrenheit. Fahrenheit was an exceptional instrument maker. He was the first person to be able to blow glass thermometer tubes of precise and even dimensions. From his little workshop in Amsterdam, he turned out the first truly accurate thermometers. And to match the precision of his instruments, he needed a new scale. But he didn't start his scale at the freezing point of water, did he? He wanted his thermometer to begin at the lowest possible temperature he could achieve. So, where did he put it? He had discovered that by adding equal parts of salt and water, he could make the liquid freeze at a much lower temperature. It made sense to him to put his zero down at that point. But this meant that on his scale, ordinary unsalted water froze at 32 degrees. Despite this quirk, we remained faithful to Fahrenheit's scale. It has fueled one of our greatest daily obsessions, the weather.
Move on with Rio's weather today. It'll be hot and sunny with temperatures reaching a scorching 24 degrees Celsius.
Celsius? What happened to good old Fahrenheit? Well, maybe it was inevitable that a scale which had water awkwardly freezing at 32 and boiling at 212 would give way to a simpler system. And after all, there is a scale which goes neatly from 0 to 100, which has been around since 1742. It was invented by a Swede, Anders Celsius, and today most countries have ditched Fahrenheit in favor of this man's scale. But how many of us really know how to convert one to the other? Take room temperature. To be comfortable, it's 22 degrees Celsius. But what's that in Fahrenheit?
74?
80, 87?
It's somewhere in the 50s.
It's fairly simple. Just multiply the Celsius number by 1.8 and add 32.
40.
It would be something under 0, around about maybe -7, 6 or 7.
I said multiply the Celsius number by 1.8 and add 32.
Double it. I would say about 72.
Good work. Normally, the air in a room is about 22 Celsius or 72 Fahrenheit. But what happens if you apply a little pressure? Squeeze all the air in a room into a thimble and the temperature soars. If you take off the pressure by letting the air expand to fill the size of a concert hall, then the temperature plummets. The relationships between the pressure, volume, and temperature of a gas were beginning to be worked out in the 18th century. The next big step came in the 1850s, when a physicist named Lord Kelvin took what was known and worked backward to a theoretical absolute. Suppose you could remove all the pressure from a gas. You'd theoretically remove all the heat from it, too. It would get colder and colder until it eventually reaches a bottom point, below which it cannot go. Kelvin called this absolute zero. It occurs at minus 273 Celsius. Down here, everything is frozen forever. Nothing changes, nothing moves, not even one single atom, ever. Luckily, absolute zero only exists in theory. It can't be reached in real life because it's impossible to get all the heat out of things. There'll always be a tiny bit left, somewhere. It may be impossible to get to absolute zero, but there is a place that is very, very close to it. Where is it? Far off in deep space? Perhaps on Neptune's moon, Triton, where there's evidence the volcanoes spew ice, not lava? No. So, is it in the Antarctic, deep under the permafrost? No. Ah, it's a little closer to home. One of the coldest places in the universe is Lancaster, England. At Lancaster University, Professors Pickett and Gaynell have built one of the best fridges in the galaxy. It goes down to within a few millionths of a degree of absolute zero. Down here, even the softest things are as brittle as glass. The physicists are using their superfridge to study the strange behavior of atoms at these extreme temperatures. And their behavior really is strange. Down here, nothing is as it is in our normal world. There is something called a superfluid which will climb up slopes. Gases are as solid as rock, and electricity flows without any resistance. The order and behavior of everything in our universe is temperature dependent. As you go up the scale, every degree has a story to tell. So get up that ladder, Professor. Go on. Minus 270 is the temperature of deep space. Minus 196. Deep freezing things around this chilling temperature can have some unexplained effects. Supercooled golf balls, for example, fly farther down the fairway. Tights, which have been chilled at the factory, are stretchier. Iced razor blades stay sharp for more shaves. And violin strings hold their tune for longer. Nowadays, we take ice for granted, but it has a long and distinguished history which goes back thousands of years before the fridge. The Romans shipped ice down from the Alps and made frozen foods. One dish, called salicatabia, was a sort of garlic and olive oil ice cream. Could you make that 2 scoops, please? Ice has always had a place in medicine. Using a frozen pig's bladder, a Victorian surgeon named James Arnott numbed parts of his patients before performing major surgery. 5 degrees is the average temperature of a household fridge. And 22 degrees is considered average room temperature. "37 degrees is the temperature regarded as normal for the human body. But in fact, normal can be anywhere between 36 to 38 degrees, depending on the person. On top of that, we start the day cooler than we end it. And we start out in life much hotter than we finish up. As far as animals go, we're pretty cool. A chicken is a roasting 41.7 degrees. So what is it that keeps us cool? A small organ deep inside the brain called the hypothalamus. It acts like a thermostat, keeping us within a narrow 1.5 degrees of our normal temperature. Sometimes it seems to lose control and our temperature soars up, with fever. Until about 100 years ago, it was thought that fever meant the body had lost control of its temperature. We now know that it is a deliberate act by the hypothalamus. Raising the temperature not only kills off many infections, but also increases the speed at which the body functions, bringing swifter recovery. Temperature doesn't just affect our bodies, it can dramatically affect our moods. Heat can make people do crazy things. There are more violent crimes in the summer than in any other season. And temperature, we're often led to believe by crime writers, can help us solve whodunits.
5:15 a.m., January the 22nd, 1990. A body is found in North London. Male, shot 3 times. A suspect is arrested. He has an alibi. The police need to know the exact time of death. Using the temperature of the body, the pathologist pinpoints the time of death between 1 and 1:15 a.m. The suspect has no alibi for this time. He is convicted of murder. Do you believe that? I wrote that as an example of the misconceptions you see in 1,000 crime novels and television shows. I'm a forensic pathologist and I write crime novels, and I know that using temperature you can't get within a few hours of the true time of death. All sorts of factors like the temperature of the environment, the posture, the body weight, drafts and wind all affect the result. When the police ask me, "When did he die, Doc?" I say, "When was he last seen alive and when did you find the body?" And it's got to be between those 2 points.
In order for water to boil, its vapor pressure, the force exerted by evaporating water above the water's surface, must equal the surrounding air pressure. In the mountains, the pressure of the air is lower, so it takes less time for the vapor pressure and the surrounding pressure to equal. Water boils at a much lower temperature than usual. When you go higher than everyday cooking, you enter a volatile realm where things melt, burn, or explode. At 357 degrees Celsius, mercury itself boils. Any higher than that, and ordinary thermometers are useless.
Let's look at those temperature scales again. Remember, on the Fahrenheit scale, water freezes at 32 and boils at 212. Celsius is divided perfectly between 0 and 100, and Kelvin is the temperature scale used in science. So remember, as a comparison, normal comfortable room temperature would be 20 degrees Celsius or 68 degrees Fahrenheit. Absolute zero, the Kelvin temperature scale is useful because it starts at absolute zero. Remember, to convert from Celsius to Kelvin, you simply add 273 degrees. So the absolute zero is a negative 273 degrees Celsius, and you can't have a temperature lower than that. Remember the video said think of absolute zero as when the atoms themselves are frozen. So atoms are in constant motion. The back and forth jiggling of the atoms is the thermal energy. So there's your first definition. Thermal energy is the internal motion of the atom. Temperature is the measurement of that internal energy. Heat then is thermal energy that is moving. So heat flows anytime there's a difference in the temperature. Because your hand has more thermal energy than the chocolate, heat will flow from your hand to the chocolate, causing it to melt. You're going to have to define those three again on the assignment. Thanks for watching.